Hello people, welcome to Roots of Unity. I am Mrinmoyee and today we will learn about the uses of substitution in polynomial equation. In our last two videos, we have learned a lot about the roots of quadratic, cubic and quartic equations. And we had arrived at the question that what should we do if we need to find out the summation of the nth power of roots, where n is a very large number, and deal with polynomials of higher orders. To begin, let us start by getting introduced with another notation for writing the sum of the nth power of roots. This is Sn. Here, the number written in place of n will denote the power to which the roots will be raised. So S1 is alpha plus beta plus gamma and so on and on. S minus 1 is alpha to the power minus 1, which means 1 by alpha, and then similarly 1 by beta plus 1 by gamma and on, depending on how many roots the polynomial has. And then we have s to the power s4 equals to alpha to the power 4 plus beta to the power 4 and so on and on. Now let's look at this equation that we had worked with in our first video of roots of polynomial equation, where we figured out p was equals to 30. It was given that the summation of the root squares, that is s2, was 32, and we had also found that s3 was 152. Now let us try to find s2 and s3 again for this polynomial, but this time in another way. Here there are two roots, x equals to alpha and x equals to beta, as this is a quadratic equation. So now we will rewrite the polynomial for each root, replacing the roots in place of x. So as x equals to alpha, we will write twice alpha square minus 16 alpha plus 30 equals to 0. And similarly for beta, we get twice beta square minus 16 beta plus 30 equals to 0. Now let us add the two and we get twice alpha square plus beta square minus 16 alpha plus beta plus twice 30 equals to 0. In other words, we can write this as 2s2 minus 16s1 plus twice 30. And from the original polynomial, we know that s1 equals to minus b by c. Here, minus into minus 16 by 2, therefore 8. Putting that value here, we arrive at s2 equals to 34. In order to find s3, we can multiply the entire polynomial equations with the roots again. So now we have twice alpha cubed minus 16 alpha square plus 30 alpha. The power of the betas also increased by 1 as well. And so when we add both, we see the s2 is shifting to s3, the s1 is shifting to s2, and finally we have 30 into s1. So we have this new equation, and as we already know the value of s1 and s2, we can replace the values and we have s3 equals to 152. So now we can keep repeating the same process, multiplying the roots across the equations to raise their powers, and then finding the summation of higher and higher powers. Therefore, we can generalize for this particular example that 2sn plus 2 minus 16 sn plus 1 plus 30 sn equals to 0, where n has to be greater than 0 because when n is equals to 0, that was our first case, where we saw twice 30 as there was no variable with 30 instead of some variable with 30. So now using the values of s2 and s3, we can find s4, which is 702. While this is a rather simple way of finding Sn of any polynomial, even polynomials of higher orders, there is one problem. To find the summation of higher power of roots, we need to first find all the previous ones. So for example, if we're trying to find S6, we would need to find from S1 to S5 all the way before getting to S6. To help with that, we have substitution. Let us start with another equation. X squared plus 3x plus 5 equals to 0 with roots alpha and beta. So now let us find the polynomial with roots twice alpha and twice beta. So if we imagine another variable for the new polynomial, say y, this would mean y minus twice alpha into y minus twice beta, leading to this. Here we see the summation and the product of the roots, which we know corresponds with minus b by a, so minus 3, and c by a, which in this case is 5, from the original polynomial. Substituting those values, we end up with y squared plus 6y plus 20 equals to 0. We can also do this in another way. As y equals to twice alpha and twice beta, and we know alpha and beta are both equal to x, we can also say y equals to twice x. In other words, x equals to half of y. Now substituting x equals to y by 2 into our original polynomial, we again get y squared plus 6y plus 20 equals to 0. This is the most used method of substitution, as it easily allows us to solve even complex problems, such as finding polynomials with roots like 3 alpha minus 4 divided by 5 and whatnot, and also polynomials with roots like alpha square and beta square. So using the same logic as before, we can say y equals to x squared, in other words, x equals to y to the power half. Again, substituting, we get y plus 3y to the power half plus 5 equals to 0. However, we cannot stop here, as we have y to the power half here. As all the terms of a polynomial needs to be a non-negative integer power of the variable, we need to change this power of half to an integer. And we know that squaring the root y will turn it into y. However, if we square the entire equation together, we will again end up with fractional powers. To avoid that, we split the equation into two in such a way that we will get integer powers when both sides are squared. So we square it, which then leads to y squared plus y plus 25 equals to 0. Let's look into another example. 2x to the power 4 minus x cubed minus 6 equals to 0, where the roots are alpha, beta, gamma, and delta. We have to find the quartic equation with root alpha cube, beta cube, gamma cube, and delta cube. And then find s6 and s minus 3 for the given polynomial above. So for the first part, we will substitute x equals to y to the power 1 by 3, leading to this equation. Again, we see that we have a fractional power of 4 by 3. To change that, we separate the terms and cube both sides. This finally leads to 8y to the power 4 minus y cubed minus 18y squared minus 108y minus 216. So this is our polynomial of the roots alpha cube, beta cube, gamma cube, and delta cube. For S6 of the original polynomial of x, we know it is equal to the sum of the roots raised to the power of 6. We can rewrite the power 6 as 3 into 2. So the cubes are raised to squares. So for a polynomial of roots alpha cube, beta cube, gamma cube, and delta cube, this is essentially S2. So what was S6 for the function of x is equal to S2 of the function of y. That is a polynomial with a variable of y. And using the general formula of S2, that is b by a squared minus twice c by a, we get this, which leads to 298 divided by 64. Similarly, s minus 3 of fx is s minus 1 of fy. So that for this quartic equation of y, this is equals to minus d by a divided by e by a. So 108 by 8 divided by minus 260 by 8 equals to negative half. And that is our answer. Thank you so much for watching the video. I hope you guys enjoyed the contents of the Roots of Polynomial series. Please leave your suggestions and questions in the comment section below. Stay happy, stay safe, and stay with Roots of Unity. Thank you.